So we're going to go over this, and then we'll get into notes today on combination circuits, which is the last type of circuit that you need to be familiar with. So we'll get through that, and then you'll have time to work on your assignment 1202.4 combo circuit problem set. So the warm-up question or questions both relate to this parallel circuit that has a 24-volt battery and 3 resistors that are 2 ohms, 4 ohms, and 3 ohms. And the first question is to find the equivalent resistance, and the second question is what is the ammeter reading at the position shown? And if you don't remember, an ammeter is going to measure amps, which is the unit for current. So it's asking for what the current is at the position shown. And this is how you would hook it up if you were actually trying to measure, which is something you'll be doing with your electric house project, is you'll have to be measuring similar to this. All right, so let's go ahead and work it out. If we wanted to find our equivalent resistance for a parallel circuit, again, the equation looks like this. Okay, 1 over 2 plus 1 over 4 plus 1 over 3. And again, we can do this by hand because these numbers are easy enough to work with. As a reminder, if you are doing this by hand, you do need a common denominator. And so looking at those digits 2, 4, and 3, our denominator here is going to make the most sense if we make it 12. And so 1 over 2 becomes 6 over 12, 1 over 4 becomes 3 over 12, and 1 over 3 becomes 4 over 12. And now we can add those numerators together. Again, if you're doing it by hand, you have to do this. Okay, and so we have 6 plus 3 plus 4, which of course is going to be 13 over 12. Again, you are not done. That is not your answer. Okay, and it's not just because it's still a fraction. That's part of the problem. But the other problem is this is not equal to equivalent resistance. It is equal to 1 over equivalent resistance. So once you get that fraction, flip it, 12 over 13, and then don't leave it as a fraction. Put it in the calculator and get a decimal. And you would get 0.923 ohms. I do want to show you really quickly as well how you could go about using the calculator to find this, and it does depend on what calculator you're using. But I do want to show you how to use the TI-84 and the TI Inspire, since that is the most common calculator that you guys are going to be using for this. So here is a TI-84, and it's actually easier in this than in the Inspire. So if you're more familiar with it, cool. If you have your own, even better. Yes, you can type the fractions, which again, this is what we're doing, 1 over 2 plus 1 over 4 plus 1 over 3. Yes, you can type it in 1 over 2, but it's actually faster to use the inverse button, and this calculator has one. I'm trying to get it to focus. There you go. And so 1 over 2 is the same thing as 2 to the negative 1 power. There's literally a to the power of negative 1 button, which is what makes this faster because the other calculator doesn't have that. Plus 4 to the negative 1, plus 3 to the negative 1, enter. Okay, and then again, we flip the fraction at the end, remember? Now this isn't a fraction, it's a decimal, but flipping the fraction is still taking the inverse. So we can do the inverse of the answer. And there it is, same answer we just got, 0.923 for our equivalent resistance ohms. So again, this one's, in my opinion, easier. There might be a button for that on here, but it's not, at least doesn't appear to be immediately visible on the front screen. So in the Inspire, I typed it a couple different ways. I typed it as literal fractions, 1 over 2 plus 1 over 3 plus 1 over 4. I also did type it this way with the power of the negative 1, but it's not a button. So if you're doing it on here, it's 2, and then you use the caret right here to the negative 1. And then you have to arrow over so that you get out of the exponent, which is why I said this one's more annoying. Plus, oops, I just did times. Plus 4 to the negative 1 plus 3 to the negative 1. Okay, and then again, you get the same thing, and then you can take the inverse of that by, again, taking your answer to the power of negative 1. I think it's faster than doing the fractions, but again, if you're using a calculator, you can try it that way. You can type it as a fraction if you want, 1 divided by 2 plus 1 divided by 4 plus 1 divided by 3. That does work as well. All right, so I just wanted to show you, now if you have a common denominator, I still think it's faster to do it this way because you can do pretty much the whole thing in your head until you get to the end. And then you're like, okay, 12 divided by 13, and that's what you type in. But it's up to you. Regardless, this is the answer to your warm-up, 0.923 ohms, and we got it with the calculator, we got it by hand. You also need to make sure you're typing it into your sheet. All right, so that was the first one. The second question says, what is the ammeter reading at the position shown? Now, again, I went ahead and added the symbol to the schematic instead of the actual ammeter with the leads. And so it's asking for what the current reading would be here because that's what an ammeter is giving us. And again, I'm going to recommend that you color code your loops. You'll notice I just added red dots for the first loop. And guess what? That ammeter doesn't measure that portion of the current. So at the position where it's located, it's only measuring part of the current going through the circuit. Specifically, if we continue color coding, it is measuring the blue and the green. Okay, again, those are the colors I picked, but it's measuring the current that goes through the 4 ohm resistor and the current that goes through the 3 ohm resistor, and only those two. It's not measuring the other portion of it. So if you were solving this, again, we've been filling in those tables. You'd be solving for those portions and then adding them together using a table, or if you wanted to just organize your calculations in some other way, you could do that. Again, we would go to Ohm's law to figure out what the current is. Now, this is a parallel circuit, so I do know that because each of my loops has only one resistor, that my voltage drops along each loop add up to the battery. There's nothing to add though, there's just one. So my voltage drop on all of these is 24 volts. Okay, we talked about that in the notes yesterday. So I know the voltage for each one is 24, and then the resistances are obviously labeled. So I can find the 4 ohm resistor. 24 equals I times 4. We can solve for the current through that component, divide both sides by 4, and of course the current there would be 6 amps. And then do the same thing for that green loop. But this time the resistance is 3. Divide both sides by 3, and I get 8 amps, and then I add them together. Okay, 8 plus 6, or 6 plus 8, whatever you want to do, okay, is going to be 14 amps, and that would be the answer to the second question for your warm-up. Okay, you can also solve it by redrawing a table and doing it that way, if you want to keep it organized in the same way we've been doing in class. All right, are there any questions about the warm-up? Okay. Please note that this current is not the total current leaving the battery. Okay, your total current would also include this red loop, and you'd have to add that on as well. Or you could use the equivalent resistance for the circuit, which we found a minute ago, along with the battery voltage, and find it that way. Okay. Again, as a reminder, we've already taken these notes, but I put it back on here since you just saw it in the warm-up. Ammeters, like the one we saw in the warm-up question, are connected in series, and they measure the current flowing through the device. A voltmeter, when you see that one, the device looks the same. It's actually a multimeter, and it measures several different types of, the ones that we're going to use are multimeters, and they can measure current, or they can measure voltage, or they can measure resistance, or a bunch of other stuff. It's always going to look like this, but the way that you connect the leads to your circuit is different. Your voltmeter is connected in parallel, and it measures your electric potential difference when there is an energy change. So it is only going to give you a value if you connect it across a resistor or a light bulb, or if you connect it across your battery. And again, when you draw them with the symbols, they'll look like that. All right, again, if you were to measure your voltage, and which is going to be your energy change per charge, like right here, that electric potential difference is going to be 0, okay, because there's nothing happening in between those 2 points. So just as a side note, and you can add it to your notes, if you were to hook a voltmeter up like this, you would get a value of 0 because you're not going to get a reading for a change. That's all that this will measure is your difference in electric potential. And so if there isn't a difference, if there's nothing happening in between, it's going to give you 0. So instead, you'd want to connect it across one of your resistors or across a battery. Again, you can see it here with the analogy we used with the color. If the color's not changing, the energy's not changing, and so whenever you try to measure it, it's going to give you 0 because that's what the voltmeter does. It measures the change or the electric potential difference, but the change in electric potential. All right, let's get into our notes for today. Combination circuits. You can see two different examples of combination circuits on my screen. It is a third type of circuit that involves parallel connections placed in series, or you have series connections on a parallel branch, either way. But it basically mixes the two types of circuits together, where you have parts of your circuit that are connected in series and parts of your circuit that are connected in parallel, hence the name combination. It is combining them. Okay, so you can see here, for example, in this one on the left, this R1 is in series with the battery, and so is R4, and yet here you have two separate loops for this parallel section. R2 and R3 are on two separate loops. So your charges would go either through R1, R2, and R4, or through R1, R3, and R4 along those loops. But part of it's in series and part of it's in parallel. You see the same thing over here. There's this whole parallel section, and then there's this one resistor in series with it. Okay, so they can look different. So before we get into our combination circuits, guys, you have to know and be comfortable with the equations for series and parallel, because if you can't do the calculations for series and parallel, then you certainly can't apply those to these new scenarios where you're having to do both. Okay, so I have a recap on my screen with what we talked about for our series circuits and our parallel circuits. If you wanted to copy it down to have it in your notes to refer to, it might be helpful. But again, as the number of resistors increases, in series, your total resistance will increase, because the equation is that your equivalent resistance is R1 plus R2 plus however many you have. However, as the total number of resistors increase in parallel, your total resistance decreases. And again, you can see that with the equation up there, because you're adding those fractions and taking the inverse at the end. And so those new resistors in parallel bring your total resistance down, but in series, they bring your total resistance up. Regarding current in your series circuit, your current is the same everywhere. Your current through, if you have three resistors in series, R1, R2, R3, your current is the same at all of them, okay, if they're in series. In parallel, however, if you have three different branches, or however many branches you have, each of those portions of the current is going to add up to the total. That's kind of what we did in the warm-up, where we solved for two of them and added them together. Okay, you could solve for all of them, add them together, and get the total. And then lastly, looking at voltage drops. In a series circuit, your voltage drops are going to add up to the battery's voltage. Again, that's one of the Kirchhoff's laws, is that the voltage drops along a loop are going to add up to the battery. Well, in series, they're all on the same loop, so of course you add them up and you get the battery. But in parallel, they're not on the same loop. Each one is on a different loop, and so each one individually is equal to the battery, because there's nothing to add it to. And so in a series circuit, your current is the same everywhere, but in a parallel circuit, your voltage is the same everywhere. Okay, within that portion of the circuit is what we're going to be doing in just a moment as we combine these two together. All right, so let's try an example. You can pretend the rest of the circuit is drawn on there. There's a battery somewhere, whatever. It doesn't matter. In this example, we have a 1 ohm resistor in series with a parallel section. Okay, so this is a combination circuit, because we have these three things in parallel, but we have this other thing next to it that all the charges have to go through. Okay, and so this is an example of combination. Your order that you're going to solve this in, you're going to start by solving for the parallel section. Okay, so we're going to look at that section with the 3 ohm, 2 ohm, and 12 ohm resistors, focusing just on this, and we're going to figure out what the equivalent resistance for that section is, treating it just like a parallel circuit from yesterday. Okay, and so we're going to use the equation 1 over 3 plus 1 over 2 plus 1 over 12. Again, you can get that common denominator and do it that way by hand. You would have 4 over 12 plus 6 over 12 plus 1 over 12, which would be 11 over 12, which is 0.9167. And then flip that, 12 over 11, 1.091. Again, I didn't show all the work because it's there's not a ton of room on my screen, but that's what we just did. Okay, so same way as yesterday, the equivalent resistance for that section is 1.091 ohms. Okay, you're going to treat that whole section like a single resistor. Again, we've been doing that. We're saying, hey, it's equivalent to this. So that whole section is equivalent to having a single resistor with a resistance of 1.091 ohms. So treat it like one resistor. And now it just looks like regular series. Now you just have a 1 ohm beside a 1.091 ohm, and guess what? You can add them together like a regular series circuit. So focusing just on that purple part now, add those together like you would for series. This time I'm not using fractions, they're not in parallel. Okay, so now I'm applying my series circuit rules, and adding those together, I get 2.091 ohms. So we had to use parallel rules to get the 1.091, and then we had to use series rules to add them together. Are there questions about that first example? That would be how you would solve for the equivalent resistance in a combination circuit that looks like that one does. Okay, now if your combination circuit instead had like 2 resistors on one of these wires, you would start there, add them together, get the total for that wire, and then do the rest of the parallel. So, I mean, you can potentially do it in a different order. We don't really give them to you like that. Most of them look like this. All right, let's try this one. Calculate the total current and equivalent resistance for the following circuit. Okay, we're going to focus on the parallel section first. Figure out what the equivalent resistance for that section is, because that section is in series with a 4.5 ohm resistor. So again, 1 over 3 plus 1 over 4 plus 1 over 12, or if you're working with a common denominator, that's going to be 4 over 12 plus 3 over 12 plus 1 over 12, which is 8 over 12, or 2/3. And then flip it, 3/2, 1.5. Okay, so again, that's our equivalent resistance for that entire section. So you can redraw your circuit once you've done that, if you want to. Okay, and that whole section is now 1.5 ohms. So now I have a 1.5 ohm section in series with the 4.5 ohm resistor. Add those together, you get 6 ohms. So the total resistance for the circuit is 6 ohms. Now, if you want to find the total current, you just have to use the total resistance for the circuit, 6 ohms, and the total voltage, 6 volts. It's in the diagram. And that's going to give you your current, because you can plug it into Ohm's law. 6 divided by 6 is, of course, 1. And so in this particular circuit, based on these values, the total current leaving the battery would be 1 amp. Now that 1 amp is going to go from the battery through the 4.5 ohm resistor, and then it's going to get to this node over here, and it's going to split. And part of it's going to go up, part of it's going to go straight, and part of it's going to go down. And those 3 are going to add up to 1. Okay, just like we talked about with parallel circuits yesterday. Then they come back together, and then they go back to the battery, and you have all of it back together. So let's fill in a table and practice calculating all these things. Now, I'm going to tell you right now, if you're using shortcuts with your tables and saying, okay, this whole column is the same, don't do that if it's a combination circuit. You can't. Because now you can't have a whole column that's going to be the same, because some things are that may be true for just series, and some things that may be true for just parallel, but it's never going to be true the whole way down for combination, because it's got both parts. So I have filled in what I know. I know my resistors are 4.5, 3, 4, and 12, and I already found my total resistance to be 6. We did that a minute ago. We also found our total current to be 1 amp and our total voltage to be 6 volts because it was in the diagram. You'll notice I also filled in 1 amp up here, and that's because all of the current has to flow through this. That 4.5 ohm resistor is in series with the battery. There's not a way around it. So that whole 1 amp goes through there, but I did not fill in the currents for the other 3 because I don't know them. I have to find them. Okay. If each resistor is a bulb, which would be the brightest? Okay, so that's the question. When we look at this, I know that my brightness depends on power. So brightness depends on the voltage drop that occurs there, and it depends on the current flowing through it. So we need to think about what's happening with the voltages and with the currents in this circuit. Okay, I know that if I was to look at the ranking for my current, I know that I have the most current through the 4.5 ohm resistor. I have to. It's all of it. The other 3, it splits. And we talked yesterday about current in a parallel circuit and the fact that your current will follow the path of least resistance. So when I compare those 3 resistors, 3, 4, and 12, they're not all going to have the same current. The 3 ohm resistor will have more current than the other 2. It's still going to have less than the 4.5 because the 4.5 has all of it. Okay, and so next would be the 3 ohm, and then the 4, and then the 12. So I don't have to do any math to rank these. I can rank my currents in order from most current to least. My most current being 4.5 ohms, my least current being 12 ohms. And then I can do the same thing with voltage. Okay, so there's my current ranking. Let's talk about what happens with our voltage drops. Again, the voltage drops along a loop add up to the battery's voltage. Those loops all have 2 voltage drops on them. Because the red loop, or let's start with green, whatever. The green loop, you're going to go through 4.5 ohm resistor and a 12 ohm resistor. On the red loop, you're going to go through a 4.5 ohm resistor and a 4 ohm resistor. On the blue loop, you're going to go through 4.5 and 3. So each loop has 2 drops. Okay, one of them happens at the 4.5 ohm resistor, the other one happens in the parallel section. All parallel voltage drops are equal to each other. That was one of the things we talked about yesterday. They're not going to equal the battery this time because now there's something else on their loop. But they will still all be equal to each other, and they will depend on the total resistance for the parallel section. Again, the parallel section had a total resistance of 1.5 ohms. We found that earlier. Okay, and so that's the total resistance for that section, and we can solve for what the voltage drop would be from there. Okay, again, if there's more resistance, there will be a bigger voltage drop. So this, it has more resistance. 4.5 is more than 1.5, so I'm going to have a bigger voltage drop at my series circuit or series component than I will at the parallel. The parallel are all equal to each other. Okay, and so I've already ranked them. I know the most current is through my 4.5 ohm resistor. I also know that I have the most voltage through the 4.5 ohm resistor. And so I can actually answer which would be brightest without doing any math, because I already know. If brightness is power, and if power is voltage times current, and if I have the same resistor that has both the most current and the most voltage, that would be the brightest one, if these were light bulbs. Okay, since brightness is power and power is voltage times current, the 4.5 ohm resistor would be the brightest. And guys, that is usually the case. If you have a combination circuit, the component that is in series with the battery is usually brighter because it has the full amount of current going through it, and because when you have parallel stuff, it makes that resistance go down as well. Okay, for that section. So it usually is, but you can always check it and do the calculations. But in this case, 4.5 ohm resistor is brightest. All right, back to our table. We can fill in what we're able to. I can calculate the voltage drop at the first resistor because I know the current and I know the resistance. So my voltage drop at my 4.5 ohm resistor is also 4.5 volts because my current was 1. And then I know that each loop has to add up to the battery. Well, each of those is on a separate loop, and they all add up to with 4.5 to get 6. So they're all the same. Again, that's one of the properties for parallel. They're not the same as the battery this time, but they're still the same as each other. 1.5, 1.5, 1.5, because each of them adds to 4.5 to get 6. Okay, and now that we have those voltages and we know the resistances, we can fill in the missing currents. You can solve for how much current goes through each section. I don't have it solved in here, but you can. Okay, and you can use V equals I times R, solve for I for each of these and figure out what your currents are, and then you can very easily find power from there. So use the table to organize it. I don't have the whole thing filled out, but you can definitely do it because you have enough information now to get through that. All right, here is another example if you just want to look at one more example of a combination circuit. You're welcome to do that. If you want to try it and see if you're right, there is a video solution recorded and it's hyperlinked. You can click on it and then you can watch that video and see if you did it right or not, or if you get stuck. I would recommend that, but I'm not going to waste time going through it all together with you because you guys need to start trying them on your own if you haven't yet. I'm hoping that you're doing it with me, but that's what I want to make sure to give you time to do because these take a little bit to solve. So try it out. Watch the video, make sure you're doing it right. And I would recommend that you do that before you get into the problem set. But we can, again, fill in the information in the table that we can see. Okay, and so we have our resistors filled in. I highlighted my parallel section. I have my battery voltage filled in. You can fill in the rest from there, similar to the one we just did. You can do that right now, or you can choose to instead work on your problem set. 1202.4, it's due by 11:59 p.m. If you'd like more practice, again, use the last slide or the one before it. Finish those 2 problems. See how you did. And then you can get to the problem set after that. If you want an even more complicated problem, there's one on the next slide. It looks like that. You're welcome to try it if you want to. Okay, I have the answers up here in the corner. So anyway, for the rest of the period, please work on your problem set, or if you finished early, you're welcome to work on your electric house RA. Tomorrow is a build day for that house RA, so please make sure that you have materials in here. But I would recommend working on your problem set first, just so that you don't have to do it by yourself when you get home. You have the rest of the period to work on it, which means that you guys have about 23 minutes. Okay, so go ahead and get to work. If you have questions for me, please let me know.